It's amazing how stories and analogies can help us understand concepts. So, as a precursor to the Open System Interconnect model, the OSI model, I wanted to talk with you for a few minutes about a story regarding how two devices or two entities could communicate with each other using the tale of two kings. I'd like you to imagine that King A wants to invite King B, who lives in a different kingdom, over to lunch. Now, do you suppose King A has to go out by himself and ride across the countryside to do the invitation personally? The answer probably is no. He's got a whole bunch of people that work for him. So in this story, King A is going to call for his scribe. Bring me my scribe. And the scribe is an entity that's providing some service to the king. In our story, the scribe is going to write down the words the king speaks, which is going to include the invitation to King B to come to lunch. And once the scribe has provided this service and written this information down, the scribe is way too high on the pecking order to have to go out himself to deliver the message. What the scribe is going to do, the scribe is going to call on the secret agent in Kingdom A, Mr. 007 himself, to go ahead and also provide some functionality. For example, 007 may provide encryption or compression or translation of that language or parts of it to make it more compatible with King B. And once the secret agent, 007, has done its work, it'll hand it over to the attorney, the lawyer, on King A's side, and the lawyer is responsible for the management and the affairs of King A, including communications between King A and other kings. So, assuming the attorney says, okay, yes, I'm willing to let this message go, the lawyer gives a stamp of approval and hands it down to the middle manager. Now, the middle manager's job is to, based on the type of message that's being sent, is to perhaps send it reliably, or if it doesn't have to have a receipt that comes back unreliably, or if the message is just too big, the middle manager may decide to chop up the message and then label those messages. For example, this is part 1 of 3, and 2 of 3, and 3 of 3. And when that middle manager has done its job, it's going to hand that message or messages, based on how it chopped them up, down to the mailroom. Now, we might think to ourselves, what does the mailroom do? Well, they handle mail. It's going to have a couple of addresses on it. It's going to have an address in the upper left. For example, that's the from address. It'd say from Kingdom A. And it's also very likely going to have a to address. For example, to Kingdom B, to King B specifically at Kingdom B. So after the mailroom has added the appropriate labels to the message or messages, the mailroom then hands these over to the envelope stuffers. Now, one of the questions might be, which is the best type of envelope to use? And that would also depend on what type of carrier are we going to use. Are we using FedEx or UPS or USPS or some other delivery service? And so if we're going to be using FedEx, it's very likely we're going to use a FedEx envelope. So the envelope stuffers are placing the messages into the appropriate envelopes. And then our last step from Kingdom A's side is the actual FedEx truck that's going to take our message or messages and route them or deliver them to Kingdom B. Now, when these messages are delivered, in our example, it's by FedEx, the FedEx driver himself or herself doesn't just run up to King B, hey, here's some stuff for you. No. King B has the same complement of individuals and staff that King A had, including attorneys and secret agents and middle managers, and mail rooms and envelope stuffers. So when the delivery happens by FedEx over at Kingdom B on the right, that information is processed from the bottom up, starting with the physical delivery of the messages, and then the envelope stuffers, which are now opening contents, and handing the results over to the mailroom, who says, yep, this is our kingdom, it's the right address, who then hand the message up to the middle manager at King B's side. And the middle manager at King B's side might be a little bit nervous. If it sees, oh my goodness, this is 1 of 3, where's 2 of 3 and 3 of 3? It might hold on to that information until it receives part 2 of 3 and part 3 of 3, reassemble all those together in one package, if you will, and then hand them up to the attorney. Then the attorney, who manages the sessions and affairs for King B, can decide whether or not we want to go ahead and continue processing these and accepting these messages. And if so, it hands it over to 007 on King B's side. So on King A's side, if 007 did features like encryption and compression on the receiving side, the 007 function would do things like decryption and decompression. And when 007 on the receiving side is done with his work, he can hand that up to the scribe. And then the scribe, providing a service to King B, would simply read off the message, which would say, King A would like to know if you'd like to go to lunch. And if King B replies, we're going to follow that same logical path from King B, going all the way down his staff, having the message delivered by FedEx, and then be received all the way up on King A's side until King A gets the reply. Now, your mission, should you choose to accept it, is to take this story that we've gone through together, and I'd like you to share it with somebody, a friend or a colleague or coworker or loved one, because by telling this story and remembering each of the staff members in the kingdoms, That's going to help a boatload as we take a deeper look into the concept of the OSI reference model and how two devices can communicate across the network. I hope this has been informative for you. And I remember hearing an explanation of how the internet worked. It went something like this. The user, sitting at their computer with their favorite browser open, puts in the name of a website, presses enter, and then boom, magic happens. Well, of course, there's a lot of additional detail and things that are going on to make that quote-unquote magic happen. And one way of helping to understand conceptually the things that are done is to use some kind of a model as a reference point or an idea regarding how something happens. And in the world of networking, one of the very popular and old models is referred to as the Open System Interconnection Model, or for short, the OSI model. And here in our infrastructure of this network, we have some computers. So let's imagine that this computer right here, computer 1, is sitting at the top of this logical stack. Or we could also say that this computer is at the top of all these layers in this OSI reference model. And these 7 layers of the OSI reference model can represent logically some of the processing and events that happen when the user on that computer in their browser presses enter, including all the steps until the actual signals are sent on the physical wires, or in the case of a wireless device, across the wireless network. And the good news is this: we can use our story of the Tale of Two Kings, along with the king's staff, as a way to understand some of the functionality that might happen when a computer, like computer 1, is communicating with another device on the network. So for our discussion, let's go ahead and call computer 1 King A. And King A is at the top of the pile here. And if this computer, playing the role of King A, needs to access a file server, for example, maybe this one right here, or a web server out on the internet, or perhaps it needs to talk to a printer, if those are all network resources, it's the application layer that's providing access, if you will, to those resources. So just like the scribe provided a writing service to write something down for King A, the application layer in this OSI reference model would make available the printing service or the file service or the web service, depending on the type of resource that King A or this computer is trying to go after. And as part of that service, if there needs to be some type of encryption or compression or translation, it's the 007 feature, or in the OSI reference model, referred to as the presentation layer, that's going to be logically providing those functions. And then as we continue to go down this logical model, the session layer is playing the part of the lawyer. And in the OSI reference model, it's the session layer acting as the lawyer that's managing the affairs and the communications for the king, or for the application that's being used. And we can consider these top 3 layers of the OSI reference model sort of like senior management. So if the session between King A, this computer, and some other device is agreed to and allowed to happen, the next logical component is our middle manager, which in the OSI reference model is the transport layer of the OSI reference model. So just like the middle manager in our Tale of Two Kings, the middle manager is responsible for reliable or unreliable delivery, depending on the requirements of the application. And it could also be responsible for taking fairly large messages and chunking them up or chopping them up into smaller pieces, and then labeling those. For example, 1 of 3, and 2 of 3, and 3 of 3. And then when the middle manager is done, it's going to hand its messages down to the mailroom, which is responsible for addresses. For example, the from address and the to address. And most addresses have a couple components, including the street name and the house number. And in the OSI reference model is the network layer of the OSI reference model that would be adding these address labels to each of the messages that are going to be sent over the network. And after those network labels are added, the messages are passed down to be put in the proper envelopes, because not every network is the same. We have Ethernet networks, we have wireless networks, we have serial networks. And so depending on the type of medium that we're going over and the protocols that are in use, it's layer 2, the data link layer, that's responsible for putting the data into the correct envelopes or frames in preparation to be sent over the network. And once the envelope stuffing is done at layer 2 at the data link layer, then the bits are actually transmitted and sent across the network at the physical layer, which in our analogy of the two kings, we use the FedEx truck doing the actual delivery. And there's a few questions that often come up regarding the OSI reference model. One is, do I need to memorize all the layers? And I would say, yes, it's going to be beneficial to you to do that. And the second question is, okay, what's the easy way to remember that? And a popular option is to create a phrase that reminds us of the first letters of each of the layers. And one of those is, please do not throw sausage pizza away. And just like when you build a brick wall, those are in the order from the ground up, from the physical layer at layer 1 all the way through the application layer at layer 7. So it would serve us to take a few minutes to practice that and write it down a few times. It would also be a great idea to jot down next to them what each of those layers logically can provide for us. And we can use the story of the two kings with each of the servants in the kingdoms to help us remember their logical function. I remember back in the early 1980s when I first started learning networking and I'd studied the OSI reference model, I was pleased as punch when I would read an article and it would talk about the application layer services of XYZ, or something at layer 3, or a new layer 2 device, because I knew the functionality of those OSI reference model layers, and I thought to myself, okay, great, that kind of gives me an idea of what that product or service does. But then it also occurred to me, pretty much at the same time, that we would be hard-pressed to find a computer that's actually running any type of an OSI reference model protocol, because the OSI reference model is just that. It's a reference model. It's not a common real protocol that we're using today. So I thought to myself, what are we using? Well, back in the day, we had lots of other protocols, including IPX, but we also had this new and upcoming protocol called TCP/IP. And TCP/IP was courtesy of the government. The Department of Defense created it. And this TCP/IP was actually a literal protocol stack, a suite of protocols working together to provide the functionalities that were described as part of the OSI reference model. And so if we put them side by side here, all the functionality in the OSI reference model regarding layers 7, 6, and 5, the application layer with network services, the presentation layer dealing with encryption and decryption and compression, and the session layer dealing with the establishment and the setup of sessions, all that functionality can be found in the TCP/IP protocol suite in the one layer called the application layer. And then layer 4, the transport layer of the OSI reference model, we usually refer to that as the transport layer here as well in the TCP/IP protocol suite. Also, it's sometimes referred to as the host-to-host layer. In either case, it's providing the middle manager functionality for reliable or unreliable delivery based on the application we're using, as well as the potential for chunking up large messages into smaller parcels or pieces. But the functionality from the model and the TCP/IP protocol suite are the same at that layer. And then as we go down to the network layer of the OSI reference model, in the TCP/IP protocol suite is referred to as the internet layer. However, the responsibilities and functions are the same as the OSI reference models, which include adding address information, like for example a street name and a house number, or in the case of the TCP/IP protocol suite, it would be a logical IP address, which we can think of as a house number and street name that allows a packet to be delivered over a network to the device it was intended to go to. And then as we continue to go down the TCP/IP protocol stack, we have this one section called network access, which includes the functionality of the data link layer and the physical layer of the OSI reference model, which would be our envelope stuffer and the correct framing for the messages and the actual physical transmission and sending of the information over the network itself. But there was one more challenge I discovered, and that was, well, if we're using the TCP/IP protocol suite and I'm reading this article and it's talking about a layer 2 device, how does that fit in? And so for the actual practical purposes, for you and I as we work with TCP/IP networks, which is the major protocol in the world today, when we refer to the actual names and layers, for layer purposes, we're going to borrow the names of physical and data link for layers 1 and 2, even though we're actually using TCP/IP. And one of the benefits of that, it allows us to be very specific when we're talking about components. For example, if we get a new network adapter and we plug it into a computer and it's physically connecting us to the rest of the network, we could say that that network adapter for that purpose is a layer 1 device. It's a physical layer device. Also for TCP/IP at layer 3, we refer to layer 3 as the network layer. So we're leveraging the name from the OSI reference model, actually renaming the TCP/IP protocol suite, the original name for that layer 3, which was internet, and simply calling it once again network. And also at layer 4, we're hanging onto the name of transport as the transport layer in the TCP/IP protocol suite. And then for everything above that, which would be layers 5, 6, and 7 from the OSI reference model, we just refer to that one big chunk of functions and features as the application layer. So as we discuss the actual use of a protocol stack, and going back to our analogy with our King A and King B, or a user like Bob sitting in front of a browser, to access the network services, those are being provided by the application layer of our TCP/IP protocol stack. And as that information is passed down this protocol stack, and each of the responsible parties are doing their work and this being sent over the network, we can use more specific terms for the data. For example, if we had the middle manager, the transport layer, that was currently working with or looking at some data, instead of calling that data, we could refer to that information at that layer as a segment. For example, a segment of data. And as that information gets passed down to the mailroom, down to the network layer at layer 3, we could refer to the data at that layer as packets. And as the network layer passes that down to the envelope stuffers, the data link layer, we could refer to the data at that layer, layer 2, as frames of data. And then as that information is actually transmitted or sent, the actual data could be referred to as individual bits that are being sent over the network at that point. So the question might come up, well, Keith, does that mean that anybody who says the word packet always is talking specifically about layer 3 of the TCP/IP protocol suite? And the answer is no, because some people use terms loosely, and we might have to take things in context. But the beautiful thing is this: you and I, going forward, if we say segment versus packet versus frame, because we know these terms, we can assume that if one of us says the word segment of data, we're referring to the data here at layer 4 of the TCP/IP protocol suite. And following that logic, if you and I were to talk about frames, we would be referring to data at layer 2 of the protocol stack. Back in 1994, I had the opportunity of working at Paramount Pictures, and I realized there's a lot of actors, and some have specialized skills, and some are better than others, and sometimes it depends on the role that the actor is supposed to play in that determines how well they do at it. Well, in the world of our protocol suite, specifically in the world of the TCP/IP protocol suite that we use today, we also have several actors or players that are part of the protocol suite. And what I'd like to do is focus on a few of the core TCP/IP protocols, and I want to start right at this point and going below, at the transport layer and working down. And at the transport layer, although there are several protocols that operate at that layer, there's two primary protocols that are used most of the time. One of them is connection-oriented and reliable, and the other is connection-less and unreliable. Of these two main protocols, the reliable one is called Transmission Control Protocol, or as its friends call him, TCP. So the middle manager at layer 4, at the transport layer, if it's using TCP, it's guaranteeing reliable delivery of the messages, or if you will, the segments that are going to be sent from this computer, or from this device on the network. And the way that TCP pulls off this feat, it does something like this. Okay, I'm going to go ahead and establish a session with this other device I'm talking to, says TCP. And I'm going to send requests and get acknowledgments. And because I'm getting acknowledgments, says TCP, I know that the segments that I'm sending are being received by the other side. And that's how the middle manager role here at the transport layer, if it's using TCP, can have reliable transmissions of those segments by maintaining a connection-oriented relationship between the local computer and the device that we're talking to. Now, what's one of the negatives of using TCP? It sounds great. It's reliable. Well, there is some additional overhead, including acknowledgments that are going to be sent and additional setup for the communications. So that's the negative side of TCP. It's a little more heavy, if you will, but it is reliable. Now, on the other hand, the other major protocol in the TCP/IP protocol suite at layer 4, the transport layer, is User Datagram Protocol, or UDP. And UDP at the transport layer, if it's being used by the middle manager, it is not set up as a connection-oriented relationship. There are no acknowledgments from the other side. So it's more like sending the segment of data and just hoping, from the transport layer's perspective, just hoping that it makes it. Because the transport layer itself is not expecting any acknowledgments if it's using UDP as the transport protocol. And a really good question that comes up is, hey, how does the middle manager, the transport layer, know if it should use TCP, reliable connection-oriented communications, or UDP, connection-less, unreliable? And the answer is, it depends on the application that is at the upper layers that's being used. So some applications are requiring TCP, other applications are requesting UDP, and that's how the transport layer knows what to use. And in either case, whether it's TCP or UDP that's being used at the transport layer, as those segments get passed down to the network layer, layer 3, in the world of TCP/IP, the one major protocol operating at the network layer is a protocol called IP, which is short for Internet Protocol. And down here at the network layer, or in our analogy of the kings, that's the mailroom, they're adding address information. Specifically in the world of Internet Protocol, they're adding IP addresses. And that's true whether we're using IPv4 or IPv6. The logic is the same. This is the part where we would be adding the correct IP addresses, both source address and destination address, on each of the packets before we hand them down to layer 2, which is going to be responsible for the framing. And as we consider the protocol suite and we learn more about it, we're going to have additional protocols that are also at play and working. But because we're calling this protocol suite something, we've chosen to name it TCP/IP. So when we see TCP/IP, it represents all the possible protocols that we might be using in this suite of protocols, which may include TCP or UDP, as well as other common protocols in the TCP/IP protocol suite. Which leads us to another question. What is another protocol? Or what is an example of another protocol in the TCP/IP protocol suite? Another example is ICMP, which is an acronym for the Internet Control Message Protocol. And if we use the analogy of actors in the world of TCP/IP, like movie actors, ICMP would be a really good supporting role. It has a lot of support services for other IP functionality. For example, if a user at computer A did a ping, typed in ping in the IP address of computer B, behind the scenes, it's actually using ICMP as the mechanism to say, hey, are you there? That would be a ping request. And if the other party is playing ball, the ICMP could also be used as part of the reply to that request, just to confirm there's reachability between point A and point B, and behind the scenes, ICMP is being used. To help reinforce the concepts of various protocols being used at various layers, let's go ahead and open up Wireshark. Wireshark is an example of a protocol analyzer that captures packets and then helps to decode them so that we can see them and make sense of them. So here in Wireshark, if we open up a capture, and I've got a capture of an HTTP session. An HTTP is an example of a protocol that would be used at the application layer when a user, for example, visits a website. And now that we have this opened up, if we just grab one of these entries here, in fact, in this example, I'm just going to grab number 4. In this output of Wireshark, it's showing us the upper layer protocols. Here at the application layer, we have HTTP, the Hypertext Transfer Protocol. And then at layer 4, we have the TCP protocol right here. And then at layer 3, the network layer, we have IP version 4. And then below that, because we're on an Ethernet network, it's showing us the layer 2 framing information for Ethernet regarding this data. If we looked at another example, let's go ahead and do that too. We'll go to File, Open, and let's go ahead and grab a DNS request. DNS is used a lot in the background when we type in a name like www.cbtnuggets.com, and it resolves that into an IP address for our computer. And the key here, if we grab one of these, we have DNS as the application layer service being used. And then at layer 4, the transport layer, here we have UDP, because that's what DNS uses for a DNS query. Then as we go down to the network layer, layer 3, we have IP once again. In this case, it's IP version 4. And then below that, we have the layer 2 information for the framing based on the type of network we're crossing. So we've looked at an example of TCP being used and UDP being used. Let's also take a look at ICMP being used. Let's open up another capture for that. So in Wireshark, we'll go to File, click on Open, and I've got one for ICMP right here that includes some ICMP traffic. So here in the Wireshark output, we have 3 panes or 3 areas. Here we have the list view, here we have the details view, and down here we have the bytes view. And up here in the list view, if we take a look at entry number 1 here, it's showing that the protocol being used is ICMP, and in the info section it's showing it's a ping request, and then it's followed by, in entry number 2, is followed by a ping reply. So with the ping request selected, here in the detail view we have the Internet Control Message Protocol. If we expand it, it'll give us the details of what's going on, including the fact that it's a ping request. And then we have the layer 3 protocol of IPv4, and then the layer 2 information regarding the framing of that data before it's actually sent out on the wire. And also, while we have a few moments right here in the protocol analyzer, let's take a closer look at TCP and UDP to compare and contrast them. Because we have UDP right here in this packet capture, let's go ahead and start there. This is an example of UDP. It's pretty straightforward as far as the UDP at layer 4. It has some port information, some length, but you'll notice here for UDP, it does not have a lot of details regarding the connection-oriented status, and that's because UDP is connectionless. It doesn't maintain connection state. It's not verifying that segments of data are making it to the other side, and that's why it's very lean and light, not a lot of overhead. However, if we take a look at a TCP segment, and let's open up another capture. In fact, let's go back to File, Open, and let's go back to HTTP, because that uses TCP. And we can click on any of these, because they're all TCP related, but we'll go ahead and click on the HTTP protocol, that being the application layer protocol, and let's expand TCP right here. So if we expand TCP, and I'll go ahead and scroll this down a little bit so we can see it, take a look at this. Just by sheer volume of all the stuff going on here in TCP, because of the reliable connection-oriented services that TCP delivers. including sequence numbers and acknowledgement numbers, and a lot of other details that UDP simply doesn't have or need, because UDP, unlike TCP, doesn't give a hoot about connection-oriented or reliable sessions from the transport layer perspective, and as a result, there's a lot less overhead, which makes it more desirable for applications and functions that don't need a connection-oriented reliable session. One of the unique challenges with phones today is that if we get a call and we have the same ringtone for everybody, we really don't know who is calling until we take another look at the phone and learn more details about it. And one solution to that is to have unique ringtones for certain callers. And in the world of networking, a computer can have many services available. For example, a web server has HTTP web services available, or a specific type of file server has files available. But when a customer comes knocking at the door looking for various services, how does that server know exactly which services the customer is after? And one of the solutions to that is to use port numbers. So as an example of this, let's use two devices. We have PC1 over here on the left and a server on the right, and they are connected over a network. And for our discussion, let's imagine this server has several services, including a telnet service that's running. And what telnet allows a person to do is to connect remotely to another system and get a command line interface. That's the telnet protocol. And if this server has some software running that provides that telnet service, it is listening for incoming requests on a specific port. And for telnet, that well-known and agreed-to port for a telnet service is port number 23. So 23 is the well-known port for a telnet server that's running the telnet service. Now, at the same time, this same server could be running software supporting web services, or HTTP. So in that sense, we could also say the server is providing an HTTP service or web service. And the well-known port for HTTP is TCP port number 80. So the question I have is, if this client over here on PC1 makes a request over to the server, how does the server know if the PC is going for web services on TCP port 80 or if it's going for telnet services on TCP port 23? And the answer is that the client, in its request for services, is going to include the port number for the service that it wants to access. So from the client's perspective, let's imagine that we have at PC1 a user like Bob or Sally or Lois, and they have some software running on their computer that's acting as a telnet client. So they're running that application, and that's taking advantage of the protocol stack that's going to allow them to reach out over the network and access a telnet service. So as this telnet client on PC1 logically is sending this information down the protocol stack on their local computer, when it gets to layer 4, it's going to use a destination port of 23. And by doing so, once that information is delivered over to the server and it works its way up the protocol stack, when it gets to the transport layer, when it sees that well-known port of 23, the telnet service is considered to be listening or paying attention to port 23, and as a result can go ahead and further process that request, that telnet request, via the telnet service running on the server. And telnet happens to use at the transport layer, it happens to use TCP. So the destination port number in the request would be as part of the TCP information at layer 4 destined to port 23, and on the server side, the telnet service is listening for TCP port 23 for incoming requests. So that would be for the request portion of our show. Now, what happens if we have a really good server? What should it do if it gets a request? And here's what I'm thinking. I'm thinking maybe the server should respond back to the client. However, if this server responds back to the client, how in the world do we make sure that the telnet server responds to the correct port back on the client? And the answer begins back with the client. When the client makes that initial request, not only is it going to include the destination port, the well-known port for a telnet service on port 23, but it's also going to include, as part of the layer 4 information, a source port. And that begs the question, well, what exactly is the source port going to be used by this client? And the answer depends on what are the available unused ports at that moment on this client, on this PC, and then it's up to the PC and the client to go ahead and choose a random unused port. So for our example here, let's imagine that the PC made a free will choice and chose the port number of 1550 as its source port. So in the initial request at the transport layer, this telnet client is using a destination port at layer 4 of 23 and a source port that it chose of 1550. So when that request comes in, the telnet service processing that request sees that the destination port is 23 on its local system and that the source port that it's coming from is 1550. And as a result, when this server responds back to the client, it's going to include in the TCP layer 4 information, it's going to include the fact that it's going to be destined to the client's port of 1550. So on the server side, it would use for the response, it would use 23 as the source port and port 1550 as the destination port. And that would be for the response from the server back to the client. So let's do one more example just to confirm. Imagine that this server on the right is running an HTTP service, and that well-known port for HTTP is TCP port number 80. And let's imagine that the PC here is making an HTTP request, and let's imagine that the source port that PC1 is using for that conversation to this server on port 80 is going to be source port number 6783. And so given this information and the discussion that we just had regarding how ports are used, I'd like you to pause the video here for a moment and think to yourself, okay, for the packet, the initial packet that's going from PC1 over to the server, what would the source and destination ports be in that initial request from the client at PC1? And then, if the server responds to that request, what would be the server's source and destination ports in the reply packet going from the server over to PC1? And here we go. Well, the PC, the source port for the initial request, is going to be port number 6783. It's right there. So we'll just put that in. And for the destination port, if it's going to the web services on the server, the destination port is going to be that well-known port for HTTP, which is port number 80. And for the reply coming back from the server back to the client, it would be these two ports for the reply traffic, but reversed. The source port would be coming from the well-known port of port 80 on the server, back to that client's initial port that it chose of 6783. I thought it would be fun to help reinforce the concepts of ports and how they're used at the transport layer by using Wireshark, a protocol analyzer, to take a peek at some of the protocols just to verify the ports that are in use. And in preparation for us looking at that together, let's cover a few well-known ports for 4 specific protocols. HTTP, the well-known port for that at the transport layer is TCP port number 80. Telnet, which is used to get remote access with a command line interface to another system. The well-known port for that is TCP port number 23. DNS, which is used all the time to make a request to resolve a name like www.cbtnuggets.com to an IP address for our computer to then use. The transport protocol and port at layer 4 for DNS requests is UDP as the protocol and port number 53 for the DNS request. And then finally here in this list, FTP, the file transfer protocol, the well-known port for that is TCP port number 21, and that's just for one component or one piece of a standard FTP request. So here, looking at a packet capture for an HTTP request, this is entry number 4, we have the client request with a source port of 3372 with a destination port of the well-known port of TCP 80 for HTTP services. And what we would expect to see, and we can find that in the very next entry, which is entry number 5, we have a response coming back from the server, sourcing it from port 80, TCP port 80 on the server, going back to the client's port of 3372. Here's an example of Telnet. So at the application layer for this entry, which is entry number 4, it shows the application layer protocol is Telnet. And then at the transport layer, we have TCP with a source port of 1550, chosen by the client, going to the well-known port of the server at port 23. And if we take a look at the next entry, which is entry number 5, we can see that the response is coming back from the server from port 23, going to the client's port of 1550. In this example, we have a DNS request. And so with entry number 1 selected here, down here in the details pane, we have a domain name system query, a DNS query. And at the transport layer, we're using UDP, which is what a DNS query uses, the source port being 32,795 with a destination port being 53, which is the well-known port that a DNS server would be listening on. And if we go to the next entry here, which is the response from the DNS server, at the transport layer protocol, we can see that the source port is 53 and the destination port is 32,795. And for our 4th example, let's take a look at FTP. FTP uses the well-known port of 21. And so if we look at the transport layer information, here we have the transmission control protocol being used at layer 4. We have a source port from the client of 1026 with a destination port of the well-known port for FTP of 21. And if we take a look at the next entry here, the one right below it, which is the response back from the server to the client, The source port from the server to the client is using port 21 as the source, with a destination port of 1026. I'd like you to imagine that we've discovered a malicious application that's running on our network. And so we talked to the security team and we asked them to block it so it can't course through the veins of our network. Now, in order to do their job and stop that traffic, it's likely they're going to need to know a few things, including, number one, what protocol or protocols is this application or this malicious software using? And secondly, what ports are involved? Because that's going to be a big part of them implementing controls to stop that type of traffic. And even for applications and services that are not malicious, it's handy for us to know some of the common protocols and ports that are used on our networks today. So here's a nice handy table I'd like to just chat with you about for a moment. On the left-hand side, we have the actual protocol itself. Then we have a little bit more information here in this column in the middle. And then over here on the right, we have some of the common, well-known ports. So if a user is going to the internet with a browser, it's very likely they're going to be using HTTP or HTTPS. The big difference is one is plain text, HTTP, and the other has security services enabled as part of it. And those protocols use TCP ports 80 and 443 respectively. If a network administrator wanted to remotely connect over to a router or a switch to do management on that, they could remotely log on and get a command line interface. They could type in characters, if you will, to that system by using Telnet. Telnet uses the well-known port at the transport layer of TCP port 23. However, because it's unencrypted, anybody who's eavesdropping or who steals those packets off the network, they'll be able to determine what's going on. So most of the time for security, instead of using Telnet, a more secure administrator would be using SSH, Secure Shell, which provides the same functionality of a remote connection to a system, but it adds encryption and security on top of it to make it more secure, and SSH uses the well-known port of TCP 22. When a computer is trying to go to www.google.com in the background, that's being translated, that name, into an IP address. And that's an example of doing a DNS query that our computer does behind the scenes for us thousands of times a day. And for that, at the transport layer, it uses UDP as the transport protocol, and port number 53 is the well-known port for the DNS server. In the world of TCP/IP, each host is going to have an address. We can assign IP addresses to clients using a dynamic protocol called DHCP, the Dynamic Host Configuration Protocol, and that uses UDP port 67 and 68, depending on if it's a packet from the client to the server or responses coming from a DHCP server going back to a DHCP client. If we want to move files around, there's lots of ways of doing it, including these three options right here. FTP, File Transfer Protocol, TFTP, Trivial File Transfer Protocol, and SFTP, which, depending on which protocol you're actually using, could be SSH File Transfer Protocol or Secure File Transfer Protocol. And over here in the right-hand column, we have the common, well-known ports associated with those three protocols. Another very common network service that's being used by millions of people every day is email. And so we have several email protocols as well. SMTP, the Simple Mail Transfer Protocol, which is being used for outbound email or email that's going back and forth between email servers. We have Post Office Protocol version 3, or POP, which is a client application used to get email from an email server. We also have a protocol called IMAP, Internet Message Access Protocol, that can be used between an email client and an email server for the retrieval and notifications of email messages. And those three protocols have three well-known ports, respectively, associated with each of them. Sometimes we need access to a remote device, and one protocol we can use to do that is RDP, Remote Desktop Protocol, and its well-known port is TCP port 3389. A lot of things we take for granted, including accurate time, and most computer systems are using in the background some flavor of NTP, Network Time Protocol, which uses UDP port 123 as the well-known port associated with the NTP server that can allow a computer to reach out, get the time, and then synchronize its own time based on the server. Another big advance over the last decade or so in the world of IP networks is to have voice traffic and telephone calls over IP networks. And one of the protocols involved with that is SIP, Session Initiation Protocol, and well-known ports associated with SIP include TCP and UDP port 5060 as well as TCP port 5061. A very popular protocol in a Microsoft network that includes the ability to receive and send files over the network is a protocol called SMB, Server Message Block, which is associated with the well-known port of TCP 445. One popular option of managing lots and lots of users in an organization is to have a central repository with all the users, Bob, Sally, Lois, etc. And then when anybody needs to check and verify things like passwords for those users, they can check with that centralized server or servers. And one protocol that can be used to do that is LDAP, the Lightweight Directory Access Protocol. There's a version that does not use security for the communications, and there's yet another version that does include the security, and that's LDAP-S, and that is for LDAP that includes the benefits of TLS/SSL for the protection of that communication when using LDAP. So the less secure LDAP uses TCP and UDP port 389, while LDAP-S uses TCP port 636. And the last protocol on the list here I want to talk about is H.323, which is a whole suite of protocols that can be used for audio and video over networks. And some well-known ports associated with H.323 include UDP port 1719, TCP port 1720, and a boatload more. And what you'll discover is that as you work with specific protocols more and more, you'll become more and more familiar with those specific ports used by those protocols. It is a nice comfort to be able to rely on something and have it happen. And so many applications, such as HTTP and SSH and Telnet, those application layer services use at the transport layer TCP. And one of the benefits of using TCP is that it's connection oriented and reliable, meaning there's going to be sequence numbers and acknowledgement numbers to validate that the communications are working between the two devices. And one of the terms that I've heard thrown around is the thing called a protocol data unit, which I just don't ever imagine using that phrase in a conversation with a friend. Instead of calling it a protocol data unit, we'd simply call it a segment, for example, if we're talking about data at layer 4. Or we would call a protocol data unit at layer 3, at the network layer, we'd call that a packet. Or at layer 2, we'd refer to that protocol data unit as a frame. And at layer 1, the physical layer, we're just dealing with individual bits. So those would be the quote-unquote protocol data units at those respective layers. And as traffic has moved across the network, various network devices focus on and pay close attention to various layers. And so for the purpose of moving a packet, for example, between one network and another, that would be a router's function. And it's focusing on the information at the network layer inside of each packet. We also have some devices on our networks called switches. And one of the advantages of a layer 2 switch is it has the ability to look at the information at layer 2 in the frames and make forwarding decisions on a local network based on that information in the frame. And then we have devices at the physical layer, like a hub or a physical network adapter card or cables, that are all considered to be layer 1 devices because they don't focus or process on anything higher in the protocol stack. I wanted to focus in this nugget also on the TCP three-way handshake, which is the magic which allows TCP to do connection-oriented and reliable communications between itself and another party. So when it comes to TCP, setting up a reliable connection-oriented session between two devices, it involves 3 transmissions, and they refer to it as TCP's three-way handshake. And to set the stage for this, let's imagine that Bob is going to be acting as a client and that Lois's computer is running an HTTP server service on her computer. So we can just imagine that Lois's computer is acting as a web server. And the TCP three-way handshake goes like this. The individual or entity that's initiating it is going to send over a SYN request. Now, that's not a SYN request like, hey, let's go rob somebody. This is a synchronization request. And I put a B here to represent that this is Bob's synchronization request that he is sending over to Lois's computer. And in the TCP header, there's going to be a little flag that's marked, a little bit that's on that says, hey, this is a synchronization. And there's also going to be a little field for a sequence number. And let's just imagine that Bob pulled from the air the number 951,057,939. And that's the sequence number it chose to use, or Bob's computer chose to use. And it sends that over to Lois. Also, as part of that TCP segment, if Bob was requesting web services, it would be going to the well-known port of TCP port number 80. And if Lois is listening on port 80 because she's running the web server software, she can go ahead and respond back to Bob. So if Bob sent a SYN request, Lois is going to send an acknowledgement of Bob's SYN request. She's going to send back an acknowledgement number that is going to be the sequence number of Bob plus 1. So the acknowledgement here should be 951,057,940. So Lois is simply taking the sequence number she received and incrementing it by 1. And when Bob receives that, he goes, great, not only do I know that she's talking to me, or the server's talking to me, but for my next sequence number, I'm going to use that 940. Because behind the scenes, that's what that really means. It's the next sequence number that's expected to come from Bob. So Bob's a happy client. He's thinking, great, she wants to talk to me. However, Lois also, the server in this case, needs to synchronize her sequence numbers with Bob, the other direction, because life is a two-way street. So as part of that reply, not only will it include the acknowledgement and the acknowledgement number, but Lois is also going to send her own synchronization request to Bob. And let's imagine for fun that Lois's computer running the web server software chose a sequence number as part of the SYN request of 290,218,379. So all that information, including the sequence numbers and the acknowledgement numbers and the ACK and the SYN flags, are all sent back in one message back to Bob, at which point Bob needs to go ahead and acknowledge the synchronization request that he got from Lois. So he's going to send a final message back. So I've got a question for you. If Lois sent over this sequence number as part of her SYN request, what would be the appropriate acknowledgement number that Bob should send back to Lois? And if we consider the logic on the previous one, the acknowledgement is going to be the initial sequence number plus 1. So if Lois's initial sequence number is 290,218,379, Bob's acknowledgement number to acknowledge that he received that should be 1 more, which would be 290,218,380. These devices can now send data back and forth. They can manage their sequence numbers and acknowledgement numbers to make sure that all the data that's sent from one party is acknowledged by the other side. And that, my friend, is how TCP establishes reliable communications by using its three-way handshake. I thought it would be fun for us to take a look using Wireshark at the actual three-way handshake in process by TCP. And so to do that, here I've got a computer with some packet captures. We'll open that up, and let's open up a packet capture that includes some HTTP traffic. And we'll focus here on packet number 1. And even before we start expanding the details of the transport layer right here, take a look over here in the info column. Here it's actually showing us the initial packet is a synchronization request. Then it's showing us that there's a SYN ACK, that's the response back, which includes the acknowledgement of the previous SYN request and the SYN request of its own, and then the third element, which is the final acknowledgement. So this is a perfect overview of a three-way handshake. We have a synchronization request, we have a SYN ACK, and then a final ACK. So let's focus on the very first segment in our TCP three-way handshake, and we'll expand the TCP information here. We'll also expand the flags. So as part of the TCP information, in this segment, it has the source port, where it's coming from, the destination well-known port of 80, and it's also showing us a relative sequence number, and it's currently set to a relative sequence number of 0 because this is our first message in the three-way handshake. But you know what I'd like to do? Let's do this. Let's right-click, and I'm going to go in here in Wireshark to Protocol Preferences, and let's go ahead, and I want to turn off the relative sequence numbers. That way we can see the actual real numbers and not just the relationship to where they are in the three-way handshake. So we'll go ahead and take off relative sequence numbers, and then we can see the full numbers. So a few things we can notice. In the flags, in this TCP header, that little bit representing the synchronization flag is set to an on. And that's how the receiving side, who receives this segment of data, realizes that it's a SYN request. Also, as part of this TCP header information, we have a sequence number, which is 951,057,939. And at the moment, there's no acknowledgement number because this is our first of our three-way handshake. So I've got a question for you. If this is the initial sequence number that's being offered, if the other side sends an acknowledgement, what would the acknowledgement number be? And if you're saying, Keith, I got this, the acknowledgement number is going to be the sequence number plus 1 during the three-way handshake. And that would be absolutely correct. So in the next packet for the acknowledgement, we'd expect to see these last three numbers as a 940, with all the previous numbers being the same. So let's take a look at the next segment, which is the response, and that's right here in entry number 2. So with that selected and the TCP information being expanded, the source port is 80, it's coming from the server, going to the destination port of 3372. That's the one the client used initially when it started the three-way handshake, as far as a port number. And now as we take a look at the acknowledgement number, look at this. As we look at that number, that's the initial sequence number from the other computer plus 1. So it's 951,057,940. The sequence number sent from the other side ended in 939, so we're upping it by 1 to 940 during the three-way handshake. And we'll also notice that the acknowledgement bit is on, which indicates that this segment of data includes an acknowledgement. And there's the acknowledgement number. The other item that's also very important about this second message in our three-way handshake is that the server wants to synchronize with the other side as well. So what the server is doing, the server has also set the synchronization bit to on, indicating, hey, there's a synchronization request here. And the server is also including its own sequence number, which in this capture is 290,218,379. So the question I have for you once again is, if the other side sends an acknowledgement, what would the acknowledgement be coming back from the other side? And now, having looked at it a few times, you might say, well, during the three-way handshake, we're going to take the sequence number, and the acknowledgement number is going to be that sequence number plus 1. And you'd be absolutely right, and we don't have to go too far to verify that. Let's go down to our third message here. In this header, there is a bit in the on position regarding acknowledgement, indicating that this TCP information includes an acknowledgement. And if we take a look at the acknowledgement number, it is this one right here, which is 290,218,380, which is perfect because the sequence number we got from the other side was 379. So by incrementing the other sides by 1 and sending it back during this three-way handshake, the other side, the server in this case, is going to know, great, my sequence numbers are now synchronized with the other party. And now going forward, they can use acknowledgements and sequence numbers to verify that all the data was successfully delivered in either direction by using the connection-oriented features, including three-way handshakes and sequence numbers and acknowledgements, courtesy of the TCP Transport Protocol.
Thanks for watching our second, and press the button below, like, subscribe, and bell icon.